Chapter 11, Part 8. So again, I don't like to read directly from the PowerPoint slide, but I'm going to do this here just to make sure that I don't miss anything. So more on action potentials. So again, action potentials are how neurons communicate. Without an action potential, the effector cell will not respond. Action potentials begin with a cell membrane that is polarized, which is the resting membrane potential, which is somewhere in the area of negative 80 millivolts. Some videos and books say negative 70. This book, I think, says negative 80. So I try to be consistent with that, but just remember that this number, this polarized, depolarized, repolarized, and hyperpolarized numbers are, generally speaking, close to that number, but not always exactly that number. Threshold, on the other hand, is usually right at negative 55 millivolts. So anyway, so an action potential begins with a cell membrane that is polarized. That is, the resting membrane potential is around negative 80 millivolts. If the cell membrane receives enough stimuli to reach threshold, enough tick, 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 ticks to bring the membrane up to negative 55 millivolts, then it will become depolarized. And at that point, when it becomes depolarized, tons and tons and tons and tons of sodium, voltage-gated sodium channels will open. And if you remember, there's tons of sodium on the outside of the cell. So if there's tons of sodium on the outside of the cell, when those gates open, tons of sodium will rush through into the cell, bringing with them a positive charge. And this causes the inside of the cell membrane to get positive, negative 30 or positive 30, positive 35 millivolts, somewhere in that area. At the same time that the sodium gates are prompted or triggered to open, the potassium channels are also triggered to open, but they're slow to open, so it takes them longer. So during the repolarized state, sodium channels become inactivated or blocked. And I'm not going to go into deep details on this just because our book doesn't, but some of the videos refer to the sodium channels becoming inactivated, so I wanted to mention it so you don't get confused. At the same time that those sodium channels become inactivated and blocked, and keep in mind that means the sodium is no longer rushing in once they're blocked. At the same time, those voltage-gated potassium channels open, and since there's tons and tons and tons and tons and tons of potassium inside of the cell, potassium will rush out through those open channels, taking with them a positive charge and making the membrane potential, or taking it to right around negative millivolts, essentially repolarizing the membrane. Now remember, those potassium channels take a long time to open and they take a long time to close. So instead of just closing right up after they let a ton of sodium out of the cell, potassium out of the cell, they stay open a little bit longer. So during the hyperpolarized state, the sodium channels reset to the closed position, and the potassium channels will stay open a little bit longer because they're sluggish and lazy. So that means they're going to let even more potassium out of the cell, making the overall charge even more negative to about negative 90 millivolts. Our book also refers to this as after potential. So how does the cell membrane go from that hyperpolarized state back to the polarized resting membrane potential kind of position or state? It does so through the leak channels that are in the cell membrane, and also through the sodium potassium pump working in the background, doing its thing. So this little image here shows what's happening when. So here is resting membrane potential right around -70 millivolts. And we get enough graded potentials, tick, 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 that changes that membrane potential enough when we finally reach -55 millivolts. This is when from here to here, tons of sodium are entering the cell, right? And when all those sodiums enter the cell, they bring with them their positive charge, bringing the overall charge to positive 35 millivolts. Those gates are blocked. Potassium gates open. Now we're losing positive charges by the potassium leaving the cell, and it stays open a little longer than anticipated. So we have repolarization, and then we're down here into the hyperpolarized or after potential state. And how do we get from here to here? Those sodium potassium gate or channels, sodium potassium channels, and the leak channels that are doing their thing. And they are basically, the cell membrane is ready to go again. So these images here kind of go over basically what I've already covered. I'm not going to go over this again. You can read through these slides to kind of get, basically more of the same. Don't forget how the membrane gets resolved at the end, how we go from hyperpolarized back to the polarized state, which is resting membrane potential. It's reestablished by those sodium potassium pumps and the leak channels. All right, so we're going to we'll keep going here for a minute. So refractory period is the sensitivity of an area to further stimulation. This decreases for a little time, and basically it means that another action potential can't fire right behind it until we get to a certain point in the existing action potential. So they're called refractory periods. There's two phases, absolute and relative. So during the absolute refractory period, it's a complete insensitivity to another stimulus. So another action potential absolutely cannot fire during the absolute refractory period. And then when we get to the relative refractory period, which is a little farther along, basically from the hyperpolarized state over to the polarized state, that's called the relative refractory period. And another fairly strong stimulus can initiate another action potential. So you should know what the refractory period is and which phases, or what phase basically an action potential absolutely cannot fire in, which is the absolute refractory period. And then just know the difference between these two. Important to note, I haven't mentioned this yet, that an action potential is a one-way street. It's going to go from the existing, or from the presynaptic neuron to the postsynaptic neuron. So it's going to go from the body or the soma to the end bulbs or the terminal ends. It's never going to go the opposite direction. This is a one-way street. All right, so we will pick up on the propagation of action potentials on the next installment of Chapter 11.